Hello everyone and welcome to our Frontier Enterprise video interview. So today we have with us Sinisa Nikolic, who is the Director for High Performance Computing and AI at Lenovo Asia Pacific. Hi Sin.
Hey Raul, how are you? Hey everybody, hope everyone's doing well.
How's it going? It's been a couple of months.
It has been a couple of months since we last year and everything's changed. The set is different and very, very cool.
Yeah, it is. It is bright blue this time around.
Bright blue,
Yeah.
Love that.
Nice. So today we're going to talk about genomics, right? So, when it comes to genomics research, it's been quite an extraordinary 5-10 years or so. Obviously, there's been massive advances in computing, massive workloads coming into being. Could you talk a little bit about, what the sort of compute landscape around genomics research over the past decade or so?
Well, it's a good, that's actually a really good question to kick off. So, look, what I would say is that the applications associated with genomics, or really omics, and omics is just the, just the terminology for all the other suite of things that one does in the genomics landscape, are what's called embarrassingly parallel. Now, I'm sure a lot of people out there know what that is, but if you don't, it really is the basis of, high performance computing is built around codes and algorithms that can run on multiple machines at the same time. So instead of taking one stream, you can break that one stream up into multiples and increase performance and throughput. Not performance, but you increase the throughput of those specific codes through a system. And so that's these omics codes. They love parallel workloads and work streams. And so in today's environment, today's technology environment, we see multi-core processors, and they spin at incredibly high rates, 3.5 gigahertz plus. We have a requirement then when you have fast processors that you need to feed that. And so you have fast bandwidth or fast channels, fast memory buses, fast everything else within the nodes or within the compute infrastructure. Fast I/O, because omics applications generate incredible amounts of data, particularly when you're doing sequencing and you're using those types of things. So generates vast amounts of data, so you need uber high I/O bandwidth. And as I mentioned before, memory. So you need ultra fast memory and you need a lot of it because these applications love memory. And so they sit in memory when they do their processing. And then they all connect together with a very fast interconnect. And then obviously you have a software stack around them where you manage the system, how do you centrally manage lots of nodes and other things. So that's effectively the landscape. And from that perspective, it's a slow burn over the last decade because HPC's been HPC for a long, long time, right? They've been the fastest of the fast at that time, working on the best of the best algorithms you can in whatever industry you're working in. But they've just gotten faster and faster and faster. The systems have increased in performance. So I'd say the size of the machines have increased, but physically they haven't, right? So floor space is reduced, allowing clients to be able to build out a little bit more, right? So, and all of that's sort of tied in with all sorts of other things around climate, data center work, and other things. So, and that's sort of where we are today as it relates to, the application areas and how technology is actually, addressing those application areas.
Yeah, I mean the HPC world is a whole world unto itself in a sense, right? So, you guys at Lenovo, you guys have worked on this thing called Ghost.
Yeah.
Right, so could you give a little bit of a background what exactly Ghost is and its origins?
So I'll go back a few years. So in 2007, I think the first whole human genome sequence was complete. And that cost about $1 million to do a single human genome sequence.
Yeah, not something you can do at scale, really.
No, and you can't do that at scale, and that'll be another point. In fact, thank you. that'll give me another bullet to hit you in a little while. And so that's one point, right? We've seen Moore's law because of that point. So over the last period of time, Moore's law has been a statement that says every 12 to 18 months we will double capacity, or the need to double capacity is required to do the same thing. So you double the capacity. We've seen Moore's law just disappear. It's now an is. Sorry, it's now a was, not an is. And we're seeing capacity of systems and capacity of data doubling every 7 months, which I find also incredible. So here we got a couple of data points. In addition to that, sequencing machines, also the sequencers themselves that live in the laboratories, they're increasing the amount of throughput. So imagine, if you will, 60 human genome sequences is about 6 terabytes. And you're able to actually sequence that across a 24-hour period now. You weren't able to do that way back in the day. When I say back in the day, 2007. Oh my goodness.
Yeah.
So anyway, so all of this is actually driving vast amounts of data, vast amounts of requirement. What are you going to do with this data? And as we've seen through COVID, these sorts of, this sort of processing work is required. So now we go forward maybe a decade. So 2007, now we're in 2017. And in 2017, to do that sort of workload, to do a genetic sequence, anywhere from 40 to 150 hours to complete with the technology that's available at the time, back in 2017, way back then.
Yeah.
So that's 40 to 150 hours. So in 2017, Intel started a project with the Broad Institute, and it's a BIS, Broad Institute stack, which is effectively the GATK codes. And they optimized and tuned that code down to 11 hours. Wowzers, we say. 40 to 150 hours down to that level, down to 11 hours.
So that's for a single genome sequence?
Yes. Now we're at a point where just some little time ago, Lenovo saw this as a distinct opportunity. Number one, to be a valued member of this community. We talk about solving humanity's greatest challenges. And this particular thing was really what instigated it, right? Solving humans' greatest challenges, looking at what's required, the vast amounts of data. And so we optimized and we tuned and we developed Ghost.
Right.
And when we'd sort of finished that, and we finished it at the time, and like all things, this is an ongoing optimization, tuning, work stream. We got that down to 11 hours. Oh, sorry, not 11, 1. Sorry, we got that down to 1 hour. So 40 to 150 hours, down to 11, now down to 1.
Yeah.
And think about that as well, $1 million to sequence, down to $1,000 to sequence. And I don't actually have the number in my head now or how much it actually costs, but it's sort of where we are roughly about today in terms of order of magnitude. So that was the driver on how we developed that. It was a requirement to generate insight or time to insight in an incredibly short amount of time, particularly in these environments where, during SARS, now during COVID, during Ebola, during all of these types of situations as an example, you need to make decisions as it relates to drug or sequencing of a virus or something that you can make human beneficial insights and directions. And that's where Ghost came from. And that's where we are today.
Yeah, I mean,
It's incredible.
Yeah, it's quite extraordinary that basically the cost came down by a factor of 1,000 nearly.
Yeah, yeah.
And the time is by a factor of 100
Yeah.
thereabouts. So it's,
Yeah.
it's quite extraordinary.
And literally, it's only getting better.
Yeah, yeah.
Literally only getting better.
But what's interesting about that is that you said you guys do it using off-the-shelf components.
Yeah,
And it's a CPU system and not a GPU system.
yeah.
So how does that
Yeah.
impact cost, and what's the secret behind that?
So, when you look at these applications, to get them on FPGA or GPUs, there's an awful lot of coding required to do that. You have very specific APIs, call-outs to those GPU systems. And so that adds levels of complexity for the user community, as well as the development community, as well as the support community. And so that was an absolute guideline that we would not do that. And when you look at bespoke or boutique type solutions for a wet lab or these small laboratories, they can be 50, 70, 80% more expensive than off-the-shelf components. So our design pretense was off-the-shelf, as you said, and so we utilized Intel processors. And what we have today is unbelievably dense nodes in our armory, I want to say, that incorporate Intel processors, incredibly fast memory, I/O bandwidth, and fast I/O subsystems. So we take all of these things, the open source GATK code that came out of the BIS, and we modified that and optimized and tuned it, and wrapped it, put a services wrapper around it, a professional services wrapper around it, where we will come in, we'll install that for a client on premise. And again, that's the design pretense. It's what I like to call off the shelf and off the charts. And it allows supportability, allows performance, and allows usability in these types of environments. And they're not massive machines, right? These aren't big machines.
Roughly how large would they be?
I'd say bar fridge.
That's pretty small.
So they sit in a 19-inch rack today, and either our base machine is 2U up to a 4U type machine. So we're not talking massive systems. I mean, Barcelona Supercomputing Center gave a quote a little while ago, and if anyone knows what the Barcelona system is, was one of the largest HPC infrastructures in the world at the time of this, at the time that they were running some sequencing. What they said was we would have needed to use the whole of the BSC facility for a number of days to sequence and to process the data that we had, that if they just used Ghost today, they would have needed a fraction an hour, fraction less than an hour to compute that. And you're talking, at that time, multiple millions of dollars.
Yep.
And we're talking here thousands, not millions.
Yeah.
So off the shelf design point allows these things, I guess, to be more commoditized.
Yep.
Or democratized, maybe that's a better word for it.
Both actually, yeah.
Yeah.
Absolutely. But you talked about installing the the machines on premise, right? So is there a specific advantage of using Ghost on premise, and what exactly is it? Latency? Is it what is it?
Well, it's a number of those facets, right? So the design pretense was on premise.
Right.
Absolutely on premise. I spoke about wet labs, laboratories, the movement of data, which, to your point, latency. Having data near where you process it is very important. I mean, everyone knows about edge computing today, so this is I guess a heavy edge, maybe, or a thick edge, or a thick edge. So you have that as a consideration. So keeping data close to where you're going to process. The second is regulation,
Right.
data privacy. You know, we all have telephones where we all have maybe a fingerprint scanner, or we have got retinal scanners in some facilities where you walk in, they'll have a retinal scan. We do blood tests, we do all of these sorts of things today. So, you know, our genetic data has the distinct possibility of being used
Yeah.
against us at some point.
Yeah.
So adhering to these data privacy laws, protecting these sequences, our crown jewels, if you will, from any potential security-related issue becomes even more important.
Yeah.
As we've seen over the last, well, let's just say 2 years,
Yeah.
the number of instances of hacking, of data leakages has increased,
Yeah.
you know, exponentially over this period of time.
Yeah.
So our design pretense was faster, better, stronger, more secure
Yeah.
than we would have in a cloud environment.
Yeah. And, you know, as you see in every dystopian sci-fi movie, you know, stealing genetic material is can be really high returns job.
Yeah.
And in some senses, it's actually more valuable in a credit card, right? I mean, you can cancel your card.
Absolutely.
You can't quite cancel your genetic code.
Absolutely.
So finally, you know, we are in the times of COVID. Thankfully, I think we are just about to open up. How does Ghost help in research about, you know, COVID or, you know, other strains that might come up in the future?
Well, I guess today, you know, the knowledge of the SARS-CoV-2 virus is a lot better than what it was, let's say, 18 months ago.
Yeah.
Right? When all of this began. That in and of itself is quite interesting and miraculous, that we have all of this knowledge. We have, you know, more knowledge of how it propagates, how it spreads. We, you know, the virus in and of itself was sequenced rapidly.
Yeah.
And that's because of all of the things that I've just spoken about.
Yeah.
The sequencing systems, the processing capabilities today. In addition to that, the collaboration between pharmaceutical organizations, these smaller wet labs, these other things, you know, was a key driver. So collaboration, so I talked about parallelization of systems. Now you have parallelization of a problem between multiple organizations. So when you look at things like, when you look at application, or sorry, you know, application type suites like Ghost and their implications here, allowed this sequencing to occur faster. It increased, or sorry, shrunk the time to insight. So as you were developing the RNA, the mRNA vaccine, your ability to test in silicon, which is another terminology, became incredibly important. So the shorter time to that insight, and that insight may be ramifications of the vaccine itself, its impact on the body. You can simulate that all in silicon, and you can only do that once that data is processed. And you process that data through Ghost, as an example. And so that's a key thing. So as we go further forward, I mean, you've seen, you know, we've seen the vaccines come out. We've now seen, I think it's just this week, the announcement of Pfizer with their pill, which is the next level of ease of ingestion and ability to propagate that to the masses for protection. I mean, this only just continues. And, you know, the World Health Organization, as an example, talks about that this is a pandemic, but it's not the first. As we all know, we had the Spanish flu, and it won't be the last, scarily enough.
Yeah.
But I think everyone out here needs to really realize that where we are today from where we were 18 months ago is amazing.
Yeah.
Absolutely amazing. And so maybe we can sleep a little bit better knowing that this technology that organizations such as mine at Lenovo have been able to put together will actually shorten the next time this happens. And God willing, that will be not for a long, long, long,
Never,
long time.
hopefully, yeah.
But you know, that is one of those things. And you know, working on humanity's greatest challenges, right? Solving humanity's greatest challenges is our byline.
Yep.
Is our absolute byline. And this is a key point on how we manage that.
Yeah, brilliant. I mean, it used to be that vaccines would take years of development. Now
Yeah.
it's like a matter of weeks, actually.
Yeah.
It's quite extraordinary. Yeah. So I think that's about all the time we have for today.
Okay.
Thanks so much, Sin. Hopefully the next time we talk about Ghost and genomics, the time will be down from an hour to a matter of minutes, and the cost will be down as well.
Well, and then we can shake hands properly.
We can shake hands properly.
By law,
as well.
we can't do it.
Yeah.
So thank you.
Thank you very
appreciate
much.
the time today.
My pleasure.
Thanks.
Thank you very much, Sin.
Yeah. Thanks, everybody.
Thanks and goodbye.
Bye.